Thank you. So good morning, everyone. So I was asked to talk about dynamics in the second lecture, and so I'll try to do that. And this is work together with Xiaoyu Zhang and the math department at Kent State University. So a quick outline of what I want to talk about goes as follows. I want to give some examples of dynamic liquid crystal systems just to give everyone a sense of the scope of the magnitude of the task, so to speak. And then I want to give a kind of an overview of what I see are the ways of doing dynamics for liquid crystals. So this is a kind of a classification scheme that seems sensible to propose. And then I'll give one detailed example that we had worked on just to give you a sense of the amount of detail and the various problems that one runs into. And then I'll close with a quick summary. All right, so examples of dynamic liquid crystal systems. So first of all liquid crystal displays are obviously dynamical. There are things going on inside. Liquid crystal is being reconfigured. And in fact, inside a projector, there's a light source. There are 3 dichroic mirrors splitting the light into different colors. And then there are 3 individual liquid crystal panels, which are like miniature displays, except they transmit light. The pixels are turned on and off. And that's how the image is generated. Maybe just worth mentioning that there are something like 4,000 times 2,000 pixels in each of those panels. So they're really high resolution elements. And each pixel looks something like this. This is basically the twisted nematic story I told you about yesterday. So incoming light goes in here as a polarizer. The liquid crystal causes the polarization to rotate and light comes out, except if you turn the switch on. So there are little transistors at each pixel. The liquid crystal molecules align, polarization, rotation doesn't take place, and the pixel is dark. And so this is happening all the time in all displays, and so this is dynamical phenomenon, obviously, the reorientation of the liquid crystal. Here's another device which is similar to a pixel but slightly different. So here, this is the field off configuration, and here the electric field causes the liquid crystal to adopt a complicated chiral configuration. Then there's an interesting story about what happens if you put colloidal particles into a liquid crystal. So imagine that you have a liquid crystal and you put a spherical particle in there where the boundary conditions are such that the director is perpendicular to the surface. So then it turns out that if the background is uniform, then line defects are formed, and these line defects will want to minimize the energy, so they will want to shorten. So these are line defects which close upon themselves, and eventually they sort of encircle the colloids in interesting and complicated ways. And so here's a kind of a scenario showing what these defects do, and this is the experimental situation corresponding to that. And so we need to be able to describe the evolution of this kind of a structure and figure out what kind of forces eventually end up binding the colloidal particles together. This is quite a fascinating story. It turns out that one can make all kinds of knotted configurations, and one can actually weave defect lines into what look like textile structures. And so here's another interesting story. So here's a colloidal particle, and this is just a laser trap. So this is just a region of space where laser light has been focused. And as I mentioned yesterday, light exerts a torque on a liquid crystal, and the liquid crystal will undergo a Friedrichs transition. So this is a distorted liquid crystal region, and this is the colloidal particle. Now normally, to move a particle with laser tweezers, the particle has to be right there in the high intensity region of the optical field. But in this case, it turns out that these two things attract each other, and the attraction is not through the usual laser trapping mechanism, but it's rather through the distortion of the nematic field in between. So again, to be able to describe this type of phenomena, we need to be able to model the dynamics. Okay, other situations are like this, where we have gold nanorods in toluene, which are aligned if a field is applied. So this is a dilute solution of essentially non-interacting particles, and if you apply a field, the field aligns the particles so they become orientationally ordered, and the optical properties change, and so you see a color change. Now, if you increase the density of particles, then they'll form a liquid crystal phase. So this is another scenario where there's interesting dynamics. So here the field exerts a torque and reorients the particles. And here's another example where there are ferroelectric SPS nanoparticles in heptane. And in this case, there's a central electrode, and the field not only reorients the particles, but the field gradient exerts a body force and changes the concentration. So here the spatially varying field changes the particle number density locally. And this is another nice example. So this is a light-driven motor made by Tomiki Ikeda. So this is a liquid crystal elastomer, liquid crystal rubber, and if you shine light on this, then it rotates. And so we want to be able to model this kind of thing as well. An interesting question is where the angular momentum comes from in this case. And I'll leave that as something to puzzle over. And finally, this is a picture of the spinnerets of a spider. So this is the belly of a spider, and it is extruding a liquid crystal polymer which gets shear aligned, and it's the orientational order of the mesogenic constituents that gives spider silk its strength. So this is another scenario that one would like to be able to model. So there's really a huge variety of dynamical phenomena that one can think about modeling. Now, I think that there are four distinct ways of modeling dynamics in liquid crystals, and so I want to describe these, but I just want to review first quickly the order parameter picture that we had yesterday. So there's this order parameter tensor, which is made up from the elements of a unit vector along the symmetry axis of rod-like or disk-like particles, and this can be in at least one uniaxial case split into an eigenvalue and an eigenvector, the director. And so one can talk either about Q or about N and the scalar order parameter S. So there are these three levels of description, basically, as I mentioned, the director model, Q tensor model, and the probability density model. Okay, now I borrowed this classification scheme from Pierre Hohenberg, who wrote this classic paper on dynamical critical phenomena quite some time ago. And they have classified a number of models which are sort of relevant in critical phenomena, but it turns out it's really useful here as well. And so I think there are four distinct possibilities. The big question is the order parameter a conserved order parameter? So this can be yes or no, and I'll talk about this a bit. And the second question is is there coupling to a conserved auxiliary field? And again, question to this is yes or no. So there are four distinct ways of doing this problem. And so the identification of these different models are historical. I don't know why it's A, B, F, and H, but I'm sticking with this model, and I also put numbers here. So this first number indicates whether or not the main quantity, the order parameter, is conserved or not, and the second is whether there's a coupling to a conserved field. And the conserved field can be anything. It can be mass, energy, momentum. Typically it's momentum, but in principle it can be anything. Okay, and so now I want to say a few words about these four scenarios. So, which are conserved and non-conserved order parameters? And so this again goes back to dynamics, Ising model, and others. And so non-conserved order parameters follow the so-called Glauber dynamics. Conserved ones follow Kawasaki dynamics. And non-conserved order parameter means that the order parameter can simply change at will at any point in space and time. There's no conservation law that needs to be satisfied. And examples are, say, magnetization or polarization in ferroelectric system. The magnetization can be anything it wants to be at any point in space and time. Okay, and so in our case, S and N and Q are all like that. They can locally change. There's no conservation law that they need to require. Now, conserved order parameter dynamics are things like the number density and the probability density, where it's really particle conservation that's being invoked. So the number density is really a conservation of particle number. And that means that not only that in the entire system the number of particles must be conserved, but it must be conserved locally. So you cannot have in a system a particle disappear here and appear here. It must actually go there, so the conservation law must hold locally. And so these are two very distinct scenarios, and so this is what I mean by conserved and non-conserved order parameter. Okay, so let's look at model A, which is maybe the most frequently encountered story, where there's a non-conserved order parameter and there's no conserved auxiliary field. And there's different ways that this story can be approached. But one way certainly is the following. So one can show that in an isothermal system, the entropy production, the rate of entropy production is equal to the rate of decrease of the free energy. So this is a rigorous result. And if the entropy production is the usual dissipative form, so this is a generalized force times a generalized velocity. The generalized velocity is q dot. The force is proportional to that, so that would be a viscosity times q dot. So this is a dissipative term. Of course, there's other ways of producing entropy, but if the entropy production is this way, then this must equal the rate of change of the free energy, and that free energy changes in time through the order parameter. And so this is a functional derivative here. And then essentially one cancels q dot, and one gets the dynamics for q in this way. And so one immediately gets essentially the simple result from the free energy. And this is just a projector basically to maintain symmetry and tracelessness. So this is a kind of a standard, straightforward way of deriving the dynamics of the order parameter in this non-conserved system. And I guess Sonnet and Hess have described this in some detail. Okay, So some examples. So one example of this kind of dynamical description is, imagine that you have a nematic cell at the transition temperature, and then say half of the cell is nematic and the other half is isotropic, and the cell is just sitting there. Now if you change the temperature, then say if you cool it down, then it will all become nematic, and this phase boundary is going to move. And to describe the motion of that phase boundary, just follow the prescription we had previously. You get this dynamical equation if you write the free energy in Landau form. And turns out this has a nice analytic solution in just the hyperbolic tangent, and you have a velocity which depends on how much the temperature differs from the transition temperature, the nematic isotropic transition temperature. So this is one example. Another example is just to look at the switching of a typical nematic cell. You have some applied field, and you can do director dynamics, again using the same approach, and then one can just bang away, get some simple nonlinear PDE, which one can then solve, and one can get all sorts of information, switching time, various other things, in reasonable agreement with experiment. So I think this model A is the most frequently used simple description that works well in many situations. Okay, now we turn to model F, when we have a non-conserved order parameter together with a conserved auxiliary field. And it turns out that things now get complicated. So we have a non-conserved order parameter, one of these things as before. And but now we have momentum conservation, so we have to enforce somehow F equals ma, which is essentially momentum conservation. The first result, as I'm sure all of you know, are by Leslie and Erickson, which coupled the director field and flow, and this is a continuum description, and one ends up with an equation for the dynamics of the director and also an expression for the velocity field. And these are two coupled expressions. Now, I will not go through this particular derivation. There are many other approaches to this with similar results, but this was certainly a landmark result, and then people have made various modifications of this. So the classical approach is to look at entropy production to establish forces and conjugate fluxes. Then one can assume linear coupling, as we already heard yesterday, and use symmetry arguments as well to identify the coefficients. And there were two schools basically proposing this: the Erickson, Leslie, Parodi, de Gennes school, the French school in the end, where they had a non-symmetric stress tensor, and the Harvard school involving Forster, Lubensky, many people, that insisted that the stress must be symmetric. And so these were two different schools, but although the formalism was somewhat different, the predictions were the same. The equations turn out to be pretty complicated, but in the end the evolution is governed by the free energy and the dissipation and momentum conservation of the fluid. And probably one of the clearest description is in the de Gennes, the second edition of de Gennes' book. So the approach then is to identify the stresses from both the free energy, the elastic stresses, and the viscous stresses from dissipation, and then construct the equation of motion both for the order parameter and the velocity field. And there are two scenarios. One can get descriptions in terms of the sort of rate of change of the director and for the velocity field. And there are also descriptions in terms of Q and the velocity field. And Ping Sheng proposed this description, which essentially follows a development which just parallels the Leslie-Erickson development, but some feel that this is perhaps not as rigorous as it might be. but these two scenarios exist. Now, there's another approach which is perhaps a bit more systematic that I think is practically useful because it gives a very specific procedure on how to get the equations of motion, and that's to use a Lagrangian approach. So the idea is that there's a Lagrangian which should be an extremum, and it conserves momentum, and if there's dissipation, then the usual Lagrangian story has to be supplemented by another term coming from the Rayleigh dissipation function. So in this story, there's a Lagrangian density, which is just the kinetic minus the potential energy density. The Rayleigh dissipation function, again, dissipation per volume. And Q is just some generalized coordinate. It can be Q or N or spatial variable. So this then gives a pretty clear procedure on how to proceed. And I want to give an example here which I think is very clear in showing how this method works. And this is a story for a solid liquid crystal elastomer, so a liquid crystal rubber. So R can be, R here is the displacement of a particle originally at position R, so this is a Lagrangian coordinate. And then the Lagrangian is just the kinetic energy associated with the motion of the mass. So the inertia associated with rotation of mesogenic units is neglected as usual, but this is the kinetic energy associated with the bulk motion. And then there is the free energy, which depends on the order parameter and the deformation, the position. And so this is the potential energy. And then in addition to this, one has to construct the dissipation function, and this is made up from all the symmetry allowed terms, and the generalized velocities here are q dot, and the rate of strain tensor, which is the grad r dot, and so one has the usual terms, and then one gets a cross term out of this. And then, having written down both the Lagrangian and the dissipation function, one can then simply proceed to get the equations of motion. And one gets immediately both the motion of the mass, which in the case of a fluid would be the rate of change of velocity here, and there are terms coming from the non-dissipative parts from the free energy, terms coming from the flow, and then there's the coupling term between the director motion and the motion of mass. Right, and this then is the equation for the director dynamics. Again, this is similar to what we had before, but here's the other term coming from coupling to the motion of the mass. And this recovers Leslie Erickson in the result of small amplitude wavelength constant S as usual. So this is just to illustrate how straightforward in principle this Lagrangian approach can be. Of course, figuring out what the coupling coefficients are is a less simple business. So here's a liquid crystal elastomer which is illuminated from above by a laser pulse, and it deforms. And this is some simulation results from Wei Zhu. I don't have the movie for this, but it reproduces relatively faithfully of what happens here, including sort of details of the deformation. You see that this surface is not flat, but it's also curved this way. All right, so that was just an example. Now, Epifanio Virga has done a really beautiful job in essentially deriving the Leslie Erickson relations using this Lagrangian approach. And I'll give a little detail here. So it's convenient to define the rotation of the fluid, omega, and then this vector n is the relative rotation between the director and the rotating fluid. This is the symmetric, A is the symmetric rate of strain, and one again has a Lagrangian as before, and then here's the dissipation, where now the viscosities are just scalar coefficients, and these are basically all the symmetry allowed terms that you can have to lowest order. And then again, just proceeding as before, putting these things into the equation above, one gets the equation of motion for the director and for the background fluid. And so this is again the standard story. This is the part that comes from the free energy, and then there's coupling to the fluid back here. Similarly, for the fluid motion, again, there's the usual sort of Navier-Stokes terms, and then there's coupling to the fluid as well. So this approach recovers Leslie Erickson. And again, it's a nice way to go because it's more general. One can include the scalar order parameter as well, and one can get a description in this way also. So, and finally I want to mention that there's another approach which is sort of similar to the Lagrangian approach, which is the Poisson bracket formalism. So that's another technique of classical mechanics, and basically it starts from microscopic variables which are coarse-grained. One has to determine the Poisson bracket, which is sort of a commutator relation between Q and the momentum density, and it recovers the Leslie Erickson, and it also obtains the dynamics for Q. And this is work by Tom Lubensky, and Tom says that it is his opinion that this is the only really strict and correct derivation of the equations of motion. So that's, he's been working in this for a very long time, and so he really believes that this is the proper way to do things. All right, so that was model F, and now I'll talk a little about model B. So this is now a conserved order parameter system, and here the idea simply is to use the equation of continuity. One can define the number density as a function of orientation, position, and time. So this is the number of particles oriented this way at this location at this time. And the equation of continuity simply says that the number density only changes by virtue of currents which are bringing or carrying particles out. Now there are two kinds of currents. There are orientational currents and translational currents. So orientation really corresponds, in the case of simple particles with a single symmetry axis, correspond to a point on the surface of a sphere, and so this is really current of those points on the surface of the sphere, and so this is the divergence on the sphere, and this is the regular translational part. And so the equation of motion for the conserved order parameter is this. This is the usual conserved order parameter dynamics. And then the question is, what are the velocities? What are the orientational velocities? And what are the translational velocities? And again, this is elucidated beautifully in Professor Doy's book. And so I recommend as a text this really very clear and delightful book, The Theory of Polymer Dynamics. So what are these velocities? If we assume that the system is overdamped, then the velocities are proportional to the gradient of the chemical potential. So the chemical potential is just the free energy per particle. So one takes the free energy, takes the derivative, functional derivative with respect to the number density, one gets the chemical potential, and then the currents are just proportional to the force, which is minus the gradient of the chemical potential, and there's some mobility, which is typically a tensor. And so these are the currents then which can be obtained from the free energy and the chemical potential. And in addition, if there are external fields, additional velocities, so additional torques or velocities arise. And this can be due to either electric fields, or it can be due to an imposed flow. If there's imposed shear flow, for example, that will give rise to an additional torque in the rotational current and additional transport in case of position. So one can then calculate these generalized currents, and then the equations of motion are simply given by this. And once rho is known, of course, everything can be calculated. So this is the non-conserved field story. And I just want to point out that if this distribution function is known, then one can calculate Q, and of course one can also calculate Q dot. And what some people do is they take the expression for rho dot, the original expression I indicated, and they multiply it by this quantity in some form, and integrate, and then they get Q dot. And then, of course, on the right-hand side, we have an expression for this. On the right-hand side, we have an expression also in terms of Q. So that's another way of obtaining the dynamics for Q. The problem there is that this expression often contains, the expression for rho dot often contains this quantity. So when you multiply through by this, you end up requiring higher moments. As we saw yesterday already, that the fourth moment is required. And if you don't explicitly evaluate rho, then one has to conjecture some closure, some approximation for the fourth moment in terms of the lower moment. Okay? But I mean, this is Alex Ray uses this kind of approach, and Greg Forrest sometimes. Okay, so the main idea though is fairly straightforward. Is just to take the equation of continuity and calculate the currents through the chemical potential and the imposed fields. And so the second half of my talk is I will give a fairly detailed example of Model B, just to indicate the kinds of problems one has to consider. And finally, we get to the last one, Model H, where there's a conserved order parameter together with a conserved auxiliary field. So in the first part, everything is the same. We have a conserved order parameter. Again, time evolution determined by the divergence of the currents. But the question is, what are the currents? And in this case, because we want to conserve momentum, we need to make sure that we are conserving momentum, at least for the fluid motion. And again, one can use Lagrangian formalism, although there's other ways to do it as well. And so the story here is just the same as before. So one can use this approach, except now everything has been taken down to a lower level, and one is talking about particles rather than the macroscopic continuum director field. And so one is looking at the motion of particles. The fluid can still be regarded as a continuum, but here the Lagrangian is 1/2 mv squared for the particles, and the potential energy is the chemical potential rather than the free energy. And the dissipation, again, it has the same structure as before. And then one can get the equations of motion by simply substituting this in here. Okay, so this is basically I think the scheme. So these are these four pretty clearly distinct ways that one can do the dynamics, and some are more appropriate than others. I have to say at this time that the systems that are becoming more and more prevalent are systems which are multi-component systems, nanoparticles in liquid crystals, lyotropic liquid crystals. And when you have a two-component system, then you really have to conserve particles. Then you really have to go to a conserved order parameter description, as in the case of Cahn-Hilliard models, say. All right. Well, I want to spend the rest of my time to talk about a model B. So this is a conserved order parameter, but no momentum conservation, just to show you the kinds of issues that arise. So we're basically interested in looking at the orientational probability, which contains all the information, and if we assume that the situation is spatially uniform, then we only have to worry about orientational current, that is a change in orientation of particles. So this is really current on the divergence of current on a sphere. And so in general, though, one has to worry about both of these currents. But in the first example, I'll consider a situation where only orientation varies. And so the question always is how to calculate the currents and how to solve the equations. So this first instance is a spatially homogeneous situation, and in fact, it's just the problem of what happens when you apply a field to randomly oriented nanorods and try to see in the dynamics what happens. And one can measure this experimentally quite well just by looking at the absorption as a function of wavelength at different fields, different times. All right, so we will describe things in terms of the number density. L is a unit vector along the symmetry axis, and so the current in this case is just the number density times the velocity on the surface of a sphere. So this is the angular velocity. And so we need to specify that and then solve for rho. So the strategy here, as I mentioned, then is to write on the free energy. And in this case, it's the simplest imaginable thing. Just the interaction term with the field. Again, we looked at this yesterday. And then there's the entropy term, which is just usual KT rho log rho. And this is the diffusive term, in fact. So the chemical potential looks like this. And the equation of motion then is that the angular velocity is proportional to the gradient of the chemical potential. And one has to project this to make sure that one is preserving the unit vector, the usual story. So that's the equation of motion. And so then one can just substitute this into the equation of continuity. And so it looks like this. Now, usually this is a nonlinear equation, although here it's linear. It's nonlinear because the field, for example, the local field depends on concentration, and also typically particles are interacting, and we didn't put it in here, but in general there would be an interaction term as well. So basically one has a problem of solving a nonlinear diffusion on so this is basically the diffusive term on a sphere, and the question is how to do this. So we have these two terms, convection and diffusion, and how to solve it. And so we need to solve this numerically somehow, and we chose to use a discretization scheme. So we needed to create a good grid on a sphere, but you can't make a regular grid on a sphere of more than 20 points. And so to make a good grid, we put points on a sphere randomly, and then we tessellated, and so we ended up making a Voronoi tessellation on a sphere. Now, this is a bit of a diversion, but let me tell you about it because it was a kind of a fun thing to do. So as a question of, well, I'm sure all of you know what a Voronoi tessellation is. Basically, you need to define boundaries so that all the points within one region are closer to this central point than to any other point. And all you have to do is draw a line between 2 points and take the perpendicular bisector and throw everything else away. And it's easy to say, but it's hard to do. It's really hard to throw away the bits that you don't need. So it turns out it's a pretty complicated problem, and there's a very beautiful scheme that was devised by Stephen Fortune while he was still a graduate student, and it's called the Fortune sweep line algorithm. And he realized that if you have points on a line, you can construct parabolas, and because the parabolas are equidistant from the point and the line, you can use the intersection of the parabolas to define the edges of these Voronoi cells. So basically you sweep the line and you construct these parabolas and you can construct the tessellation. And it's a really beautiful and elegant way to do it. And so this really kind of inspired us, and we decided to do this on a sphere. And so it's an interesting project on a sphere because, first of all, what's a parabola on a sphere to begin with? But anyway, it turns out that one can do it, and it's a nice way to tessellate the sphere. So here's a tessellation with 100 points, and there's this nice Euler formula relating the number of vertices and edges and faces, and for spheres and equivalent things, this has to add up to 2, which tells you that you can't have all hexagons, for example. You have to have some pentagons and so on. So anyway, we came up with an algorithm of Nlog order Nlog n, and we got it up to 1,000,000 points. We're pretty proud of this. So it looks like this, and one can then count the different polygons up there, and hexagons are the most popular, but there's quite a distribution. Anyway, so one then has now a structure, but it turns out that it's not very regular, so it's useful to regularize the surface. So basically one can move each point to the centroid and then repeat the tessellation again, and then one can get a very nicely regularly tiled sphere with mostly hexagons and 12 pentagons, and I think that's as regular a lattice as one could put on a sphere. Okay, and then how to get the equations of motion. So the idea then is one can look at the average density inside each cell and then figure out the rate of change just by looking at the current flow, and then one can integrate this, and one can just basically see how much current flows through the boundaries. So it's a relatively straightforward procedure. So the area times the average number density inside is just equal to the current multiplied by the length of the different edges that it flows through. So one can write down, one can do explicit time stepping in this way and calculate the time evolution of particles. So it's pretty straightforward, and the flux is made up of 2 components, a convective and a diffusive part, and so we treated these independently, and I don't know, we did so this is, we go to some intermediate concentration due to convection, and then do the remaining step due to diffusion. So we did fractional time stepping, and I don't want to go in too much detail, but it's a relatively straightforward way of just doing backward Euler on the diffusive part, and just doing explicit upwind scheme just to look at the current flowing in one direction for the convective part. So it's a relatively straightforward scheme, and so here is a picture of what happens when you apply a field. Originally you have a uniform distribution, and then you see that the distribution peaks at the two poles, as you would expect. The field is in this direction. So one can get reasonably decent dynamics in this way. One can then calculate the probability density and see how it evolves in time. And again, nothing really surprising happens here. It's pretty much as one would expect. Now, it's also interesting to look to see what happens if one is a spatially inhomogeneous system. So we looked at the case of electrically neutral nanorods without dipole moments in a non-uniform electric field. And here we get particle translation as well as rotation due to radial force, because the field goes as 1 over r. And the mobility is anisotropic because rods can translate easier along their long axis than in directions perpendicular to that. So this is a kind of a cloaking example of the situation I described. There's a wire inside a capillary tube, and it's surrounded by suspension of gold nanorods. And and if you watch the red line, which is the wire, carefully, you see that it sort of appears and disappears as the field is applied or not applied. And if you look at the optics, then you can see that there really is a kind of a cloaking phenomenon, that the light wave is guided around the wire. So, right, so we try to model that. We need to put in the translational current as well as the orientational current, and so the translational current is just average, so number density times average local velocity in addition to the orientational current. And again, we have a tensor, mobility tensor here, and one can then get the chemical potential from the free energy, and the chemical potential gradient. Chemical potential gradient gives a force to drive this current due to the spatial variation of the electric field. So here's the order parameter, the two principal components, as it evolves in time as a function of distance from the central wire. And here's what the density function looks like as a function of time. Now, an interesting thing happens if the translation is faster than rotation. One can get this curious phenomenon that the order parameter becomes negative near the wire, and this is associated with the fact that particles which are pointing towards the wire get transported out very rapidly, leaving behind particles which are all pointing the wrong way, so to speak, with a negative order parameter. So one has this funny thing which is a kind of an orientational hole burning. So initially you end up with getting an inverted distribution, and this phenomenon is seen in some optics experiments when the optical field essentially changes the distribution function at the beginning in a way which is maybe at first glance surprising. So one can get quite a lot of interesting dynamical information from this story. Now, visualization is a real problem. So we're trying to visualize a tensor field in 3D, and it's really difficult to do it effectively. Here, this we attempted to do a picture. This is a wire in the middle, and these spheres, the coloring on the sphere shows the distribution function, and you can see that for a sphere, so you can see that the spheres kind of go around in circles. So here you can see that the distribution function is peaked at the 2 poles and less so as you move out. But I think to have an effective visualization of the order parameter tensor field is really a challenging problem. So we also did this for these ferroelectric particles. So this is our simulation, and although it's not exactly the same as time scale as this, I think it shows essentially the same type of behavior. Okay. Now we wanted to see if we are getting results comparable to other people, and Greg Forrest have studied liquid crystal polymers for a long time in shear flow in a lot of detail, and they got a pretty complicated phase diagram with very sophisticated behavior. And they used spherical harmonic expansion instead of the kind of discretization that we did. And so this is the phase diagram where this is the strength of the nematic interaction, and this is basically the dimensionless shear. And so we can essentially reproduce all of this, and we looked at some detail at this region here where there's this funny kayaking behavior. And so in that case, the director field kind of oscillates in direction under the influence of the uniform shear. So that's pretty much what I wanted to say. So let me try to summarize quickly. So orientational order is ubiquitous, and therefore dynamics is really important. So there's these different order parameter pictures, but the point I really want to stress is that I think that given the emerging systems are being what they are, I think these conserved order parameter descriptions are the way to go, because otherwise the non-conserved order parameter scenarios cannot deal with non-constant number density. And so I think that that's a real issue. And these conserved fields may be needed depending on what you have. If you have fast dynamics where the fluid, where the fluid inertia is playing a key role, then one has to conserve momentum. There are situations where one needs to conserve energy, and one needs to have another conserved auxiliary field. And but the point is that all of this can be done, I think, consistently within this framework, certainly through the Lagrangian formalisms. And I think describing systems, both multi-component systems and particles with higher symmetry, present real challenges both in modeling and in computation. Thank you very much.
Are there any questions?